I'm picking up where we left off today morning. And the last topic we saw was that neural networks can kind of overfit to data in this absurd manner. And instead of giving you a function like this, the smooth curve we would really want in a setting of this kind, they can give you something that rises very steeply up and down. And this is not behavior that we would really like. And so the reason for this we saw was because individual neurons can be made to have the activation output of individual neurons can be made to rise arbitrarily steeply by just increasing the magnitude of the weights. So even if you're thinking of a ReLU, right? What does the activation of a ReLU look like? What does the ReLU activation look like, guys? Max 0x, right? You're plotting this. Why is this not working? This mouse is supposed to give me a sec. For some reason, it's not. Pointer option is a pen. So let me try drawing this with a mouse. So a ReLU looks something like this, right? But then just before the activation, the affine terms. So you have the activation, and then below the activation you have this pen is not working. Strange. Makes my tablet useless. Okay. And below the activation, you first have all of the weights of the incoming edges, right? And the weights of the incoming edges, these could be scaled up. And scaling up the weights of the incoming edges would increase the slope of the ReLU, and you can make the ReLU arbitrarily steep, right? And so what we wanted to, and that allows us to model crazy functions of this kind. And so what we wanted to do was to restrict the speed with which these activations could rise. And that meant we wanted to put a limitation on the weights. You want the weights to be low. And so the way we did that was that to the standard activation function, we also added a second term, which was simply the squared norm of the weights, weighted by some lambda. So since you're minimizing this loss, you would simultaneously be minimizing this average divergence and also the weights. And then when you perform gradient descent, this term is what you would be taking the derivative for. And so that's going to be the derivative of the first term, which is your standard loss, plus when you take the derivative here, the 2 comes out, 2 and 2 will cancel. It is going to end up with lambda times w. And so this modified derivative is what you would be plugging in to your gradient descent rule, right? This guy here. Make sense? Right? And so that, I'm not sure why my pen is not writing. It should be writing. Lambda is something that you would fix. And so if only, so this is going to be, if I can write, that's going to be, right, WK minus the standard eta times the standard derivative, right? The gradient minus lambda times WK, right? So this is what we get, because this term here, the second term is the derivative of this guy. And so when you group it all up, I can just write it as 1 minus lambda times WK. So I'm grouping these two terms. And the second term is just the standard derivative that you get when you minimize your loss function. And so using this external regularization, which minimizes the weights, is the same as typically lambda's a value between 0 and 1. So it's the same as shrinking your weights by a factor 1 minus lambda before you make the adjustment. So this one implicitly actually makes sure that the things don't get too steep. And we've already done this, right? What did we call this in your homeworks? What did we call this business of shrinking the weights? You must have done it, right?
Weight decay.
Weight decay, right? And you're decaying it by a factor 1 minus lambda. So this was just one way of regularizing. So basically in your standard update rule, you're now going to be using a decay parameter that scales your weight before you make your adjustment. So, so far so good, right? Everybody with me so far? Any questions? Questions? No. Okay, so I'm going to move on, right? There's another way of actually imposing smoothness, and this is through network structure. So smoothness constraints can be imposed through the network itself for a given number of parameters. If I redistribute the same number of parameters in the form of a deep network versus a wide and shallow network, then you get smoothness, because each layer sort of warps the output of the layer underneath it. And if you have any restrictions of the weights, if you don't let these weights just scale up arbitrarily, then each subsequent layer is going to be working on the warped surface, but it can only, instead of making these peaks and valleys steeper, it's actually going to make it smoother, particularly if you've got any kind of regularization of the weights. And so as you go through the network, the surface of the function that the model captures becomes smoother and smoother and smoother. Does this make sense, guys? Yes or no?
So does this mean that like the first layers in the network captured kind of like sharp edges or fast changes, and then the deeper layer kind of like captured the smoother kind
so
of like
no.
changes?
So basically what happens, imagine I have some kind of a restriction on the weights, right? Again, this only works when your weights are restricted. So if I have any regularization of the weights, then the weights are not going to have introduced arbitrary slope. The slopes of all of these layers are going to multiply, right? So imagine you have a linear layer. This weight matrix is going to increase the slope of your function by a value that's at most the largest singular value of this weight matrix. That slope is going to be further modified by this weight matrix. And so the largest slope of having of a network with two layers is going to be the product of the largest singular values of both weight matrices. So as you keep going through the layers, the slope is capped by the product of the singular values of the weight matrices. And even if you don't have an upper bound on the weight matrices, the properties of matrices is that when you plot out the singular values, they're going to have a very small number of large singular values. The majority of them are going to be small. You know this as a property, right? Yep. And the only time things are going to keep magnifying is if the singular vectors of all of these weight matrices line up. Although typically they won't. So a direction that gets magnified by this weight matrix is going to get squished by the second matrix. So the net effect is that as you keep adding layers, the overall function gets less and less peaky and more smooth. Does that make sense?
Yep. Thank you.
Okay. And so for a given number of parameters, if you just redistribute the parameters to make the network deep rather than shallow and wide, you're going to get, just through this business of depth, as a statistical property, the function is going to get smoother and smoother. And you can see how that works in this example. So, Masa, did this make sense to you?
Yep.
Right? And so we prefer deep networks. So here's an example. This was, even if I know the optimal architecture of the network. It's hard to train it. So here are a couple of different decision boundaries. We drew 1,000 samples from each of these and tried to train a network with the optimal architecture. The optimal architecture is going to have two subnets with 4 and 3 neurons, and the two are combined by a final output neuron. When you train it, regardless of how you train it, the decision boundary you end up running is this garbage to the right. Same thing for the figure at the bottom. So just straight up training doesn't help you get anything, right? Now here, we are not actually performing any kind of weight regularization in this example. We were trying to learn a decision boundary that looks like this bolt in the first case and like this bear in the second case. And we have 660 neurons in each case. When they're arranged as 3 layers of 220 neurons, this is the decision boundary it gets. If I arrange it as 4 layers of 115 neurons, it gets this decision boundary. If it's 6 layers of 110 neurons, it begins to look like a bolt. By the time I get to 11 layers of 60 neurons each, it actually looks like the bolt that I was trying to capture. So just rearranging the same parameters in depth versus breadth gives me the kind of regularization that gives me smoother decision boundaries. Is that a convincing example over here? Just visually? Yes or no? Questions, guys? Okay. And here's another way of improving your actually obtaining smoothness. And the way to obtain smoothness is to simply have a lot more training data. If you have a lot more training data, then the ability of the network to behave like this gets compromised. And so simply having 10,000 training instances in this example actually gets me the bare outline. But then you're never going to get the kind of training data that would allow you to simply learn the function without regularization in real life. So the story so far: gradient descent can be sped up by incremental updates. Convergence can be improved using smooth updates. The choice of divergence affects both the learned network and the results. The covariate shift between training and test may cause problems and can be handled by batch norm. And again, batch norm will not really work if your problem or your network is of the kind where it does not introduce covariate shift. If it doesn't introduce covariate shift, you're gaining nothing from batch norm, besides maybe shrinking the derivatives a little bit and causing issues. And finally, data under specification can result in overfitted models and must be handled by regularization or more constrained, generally deeper network architectures. So, questions? No, okay. So there have been other techniques that have, even if the training data are very diverse, yes, all of these still hold. Batch norm will work if your training data are diverse, but even there, it depends on the problem, because if your network tends to sort of compact the space, then your mini batches will begin to overlap, and then you're not going to gain very much from batch norm. Now, other techniques have been proposed to improve the smoothness of learned functions, like L1 regularizations of network activations, adding noise, and so on. Of these, the most influential method that you have also encountered is dropout. What is dropout? Dropout is based, the underlying principle of dropout is based on a machine learning technique called bagging. How many of you have heard of the term bagging? Anyone? Have you heard the term bagging? If you have not heard the term bagging, then just say no.
No.
Okay. So it's basically a voting scheme, ensembling scheme, right? In your homework, you might have encountered that if you train many different networks and average the results, you get a better performance than if you just train one network, right? So in general, this principle holds. So given a collection of training data, we will train even if you're training the same kind of model, for example, a decision tree, you will train many of these, many different ones of these. And so if you're using a given set of training data, the way you train many different models is by sampling the training data repeatedly. So each time you get a different sample. And the objective is that at the end, you get many different classifiers. Now, given any training instance, that would be classified by all of these classifiers. And the actual prediction you're going to make is based on a vote. This is the simple idea of bagging. And it works really, really well. And it's very simple. Originally proposed by Leo Brand. Did that concept make sense? Guys? Okay. So now, in our neural network, when you perform dropout, during training, for each input, at each iteration, you're going to turn off each neuron with some probability 1 minus alpha. So if this was your network, you're going to flip a coin whose probability of heads is alpha for every one of these neurons, including the inputs. And if it comes up a heads, you keep it. Otherwise, you delete it from the network. And the manner in which you delete it is you don't actually need to delete it. You just set it to 0, right? In practice, you just set it to 0 according to the failure of a Bernoulli random number generator with success probability alpha. That's the equivalent of a coin flip with P of heads alpha, right? So if you have, this is going to be done afresh for each training instance. So for training instance X1, you'd be flipping all of your coin, flipping the virtual coin and switching on and off neurons. And then for training instance 2, you'd be doing it all over again. And for training instance 3, you'd be doing it all over again, which means that each of the training instances is actually going to be seeing a different network. And because you do it each time, the next time, in the next epoch, training instance X1 is going to see a completely different network. So the odds are you will never see the same network twice during your training. The process makes sense? Yes or no?
Yes.
Okay. So what exactly is happening? Suppose I have a network with n neurons, right? Each of them can be switched on or off. And so, starting with a network of this kind, how many networks of this kind can I construct if the new network has n neurons? Anyone? How many can I construct? 2 raised to n, because I can switch these. There are 2 raised to n different ways of switching on and off these neurons, right? And we are speaking all the way only till the feature layer. Obviously, you're not going to be switching off neurons in the class output layer. And so there are 2 raised to n possible subnetworks obtained by choosing different subsets of nodes. So basically what is happening is you're using this original network as a template, but from this original network, you're actually treating the original network as a collection of 2 raised to n different classifiers. And each time you flip your coin and turn things off, you're basically sampling one of these 2 raised to n possible networks. Does that make sense? Right? Then with the rest of you, did that make sense? Right? And so effectively, what dropout is doing is learning 2 raised to n different networks. They're not independent because they share parameters, but it learns 2 raised to n different classifiers simultaneously with shared parameters. Okay? And so that's the statistical interpretation, but there's also a mechanical interpretation, which is this. Now consider this network to the right. So if I train this just anyhow, then there's a complete and in fact very non-zero probability that something that actually happens very frequently, that in some early layer, the layer simply learns to copy the input of the layer to the output. For example, in this figure, this bottommost layer may simply copy the values from the input to the output by setting these weights to 1 and all the other weights to very low values, right? And so what will happen is that effectively you lost a layer because now the rest of the work is being done by the rest of the network. And that's a perfectly valid thing to do, but it's not something you would want. Is that clear that this can happen? Right? So what dropout does is that when it switches things off randomly, then for many of these neurons, there is no value over here for it to simply copy over. So these neurons are now forced to rely on adjacent neurons. And so by switching things off, you are forcing the neurons to have a receptive field that is wide and preventing this sort of an implicit collapse of layers of the network. So dropout forces the neurons to learn denser patterns with redundancy. So this is the actual mechanical explanation as opposed to the statistical explanation. Does this make sense? Yes or no? Right. And so there are these two different explanations, right? And both are related. And so how would you actually implement dropout? When you're going through the network, at each layer, you're just going to go through all of the neurons and flip a virtual coin. And if the virtual coin comes up with 1, which can take a value 1 or 0, then you create a mask, which is simply the output of this virtual coin. And so if this virtual coin has a probability of success alpha, then some fraction alpha of the neurons in the layer are going to have a mask value 1. The rest of them are going to have mask value 0. And then when you compute the output of the network, you just multiply it by the mask, and any elements, any neurons for which the mask value is 0 are basically going to get switched off. So there's just one extra step when you're performing your forward pass. You're computing a mask and multiplying the neuron outputs with a mask. And when you're performing back propagation, you're going to do the same thing. You're going to retain these masks in the forward pass because the mask tells you which neurons were switched on and off. And in the back propagation, remember, back propagation looks a lot like forward prop, right? So once you compute the derivatives at each layer, you're going to multiply them by the mask again so that you switch off the contributions of neurons which didn't actually contribute to the computation. And so only the remaining derivatives. This mask will effectively zero out the neurons that were not used for that instance. And so the derivative computation is just going to use the subbit that was that was used by that particular instance. So did this make sense? This very simple concept of how you would implement it. Yes, no questions? Right. So I have one yes. The second one, before I move on. Does anybody else have any questions? Or can you at least give me a yes that you got it? Okay, 2. All right. So now, what about evaluation? So now when you're evaluating things, remember what you're actually learning here is 2 raised to n independent networks. Not independent, but shared parameter networks, right? You're implicitly learning all 2 raised to n networks. So when you perform classification, what should you be doing? Using the bagging principle.
Turn it off.
Pardon me?
Turn it off.
Turn it off? No.
Sorry, in classification. In classification, yes. Turn it off. Okay.
There's no turning it off, right? I have a bag of 2 raised to n networks, right? So what would I be doing for bagging? Yeah. How did I deal with it? Over here.
Have like a majority vote or...
I did a majority vote, correct? So in other words, you're going to be, what you would really do is to compute the output using each of these 2 raised to n networks and average their outputs, right? That makes sense? Yes, no? Right. So basically what you want to do is this. You want to take an expectation over all of the networks, right? It turns out that taking this expectation over all of the networks is a really, really complicated thing. And then here we use an approximation. So I'm taking an expectation over a function of neuron 1, neuron 2, and so on, correct? So these are all the neurons in the network. This is what I'm taking the expectation of, but this is hard to compute. So I'll make an approximation. I will say this is the same as the function of the expectation of the individual neurons. This is N1. I'm trying to write with a mouse, so pardon me, right? My pen isn't working. That's the number 2, and so on. Did this make sense? The approximation I'm making, is it clear? Right? Instead of taking an expectation over all the functions of neurons, you're taking the function of the expectation of neurons. Are these two going to be the same? Anyone? Guys, are these two going to be the same?
If they are independent, they would be the same.
In general, even for the simplest thing, the expectation, let me try to write this. And so the expectation of f of x, right, is not equal to, not f of expectation of x. So think of a, for example, let's say f of x is simply a quadratic and x is a Gaussian random variable. So f of x is x squared. X squared is always positive, correct? And let's say x is a Gaussian random number with 0 mean. Then what would this term be? It's going to be a large number. This is going to be the variance of x, because you're basically taking the expected value of x squared, right? Let's say x is a Gaussian with 0 mean and unit variance. And f of x is x squared. So expected value of f of x is the expected value of x squared. And that's going to be sigma squared, right? Yes or no? Guys, I just have one yes. So, Masa, why is that a no? Because f of x is x squared. So this is going to be the expected value of x squared. What is the expected value of x squared when x is a Gaussian with 0 mean? That is just the variance, right? But what is the f of expected value of x? What is expected value of x over here? That is 0, right? And so f of 0, where the function is x squared, is simply going to be 0. So you can see that the expected value of f of x is not going to necessarily be the f of the expected value of x. Is that making sense? From this simple example? Guys? Anybody else? Did you get that? Okay. So going back to, so now are these two going to be the same? the average of the networks, is that going to be the network of the averages? It is not. They're not going to be the same, right? Unfortunately, we can't really compute this expectation, so we are going to be using the second term. And so we're going to say that the expectation, the average over all of the 2 raised to n networks, is going to be the network of the expected value of the individual neurons. This is an approximation. But then now you can go and look at the individual neurons. And the individual neurons were simply the activation multiplied by my Bernoulli random variable, right? D is the Bernoulli random variable, which took the value 1 with probability alpha. What is the expectation of this guy on top? Anyone? What is the expectation of this guy on top? The only random variable is D. What is that going to be? Can someone answer me? D is a Bernoulli random variable with probability alpha. So what is the expected value of D?
Alpha.
How many of you agree that it's alpha? Okay. Do you agree that the expected value of D is alpha? Yes or no? Just give me a yes if you believe this. Guys, right? And so this means that the expectation of yi is simply going to be alpha times sigma, right? You see why the second equation holds? This term? Do you see why this holds? Yes or no? Yeah, okay. So what this means is that if I'm using this approximation, that the average of the networks is the network of the averages, then all that means is that I'm going to be replacing each neuron by alpha times the activation of the neuron. Basically, at each of these neurons, when I compute the output, I'm going to multiply by alpha. That's it. So when I perform dropout with probability alpha, meaning the probability of dropping out is 1 minus alpha, and the probability of success is alpha, then during inference, I must multiply the outputs of all of the neurons by the term alpha. And that is going to be my solution. Now, that can be done in a bunch of different ways. You can explicitly compute the activations and multiply them by alpha. Or you can multiply the weights of the next layer by the term alpha and just say that after training, I'm going to multiply all the weights by alpha, right? Multiplying the activation by alpha is the same as multiplying these weights by alpha as far as the next layer is concerned. And so you can either multiply y by alpha or multiply all the weights by alpha, or during training, I can pre-multiply all the activations by alpha inverse and not do anything during inference. All of these are equivalent. But the bottom line is that what we are really doing is that we are multiplying the outputs of the individual neurons by alpha. And is that the accurate thing to be doing? Is that the theoretically correct thing to be doing? Yes, no? No, it's an approximation, right? Because what we wanted was this guy. What we are computing is this guy, and that can be computed by multiplying the activations by alpha. And that's going to be dropout. I just have some pseudocode for how you do this. And sometimes dropout will not work. And dropout will not work when the gap between the expectation of the network and the network of the expectations is very large. Now, it's not easy for us to know when that gap will be large. And so we just use it and try to empirically poke around to figure out whether dropout is working in any setting or not. But in many situations, you'll find that dropout doesn't help you. And the reason for that is that you're not really bagging on that particular network. The function has gotten to a point where the expectation of the networks is not the same as the network of expectations. Nonetheless, when you actually use dropout and it works, here are the results from Nitish Srivastav's first paper on the subject. You can see how the classification error plummets when you use dropout, as opposed to not using dropout, but it plateaus pretty quickly. Because what is happening with dropout is that you're effectively bagging. You're using a large number of classifiers and averaging. And that gives you this improvement in performance. That makes sense? Everybody with me? Anybody else? Give me some yeses, guys, so I can move on. Perfect. Okay. And so there are many variations on dropout. There are things called zone out, drop connect, where you drop individual connections. Zone out is where your randomly chosen units remain unchanged across the time transition. Things called shakeout, with scale up weights of randomly selected weights. Whiteout, where you multiply weight dependent Gaussian noise to the signal on each connection. All of these are basic variants of the same basic idea, which is that you're basically shaking the network and creating a statistical collection of networks over which you're averaging. Right? So the story so far is that gradient descent can be sped up by incremental updates. Convergence can be improved using smooth updates. The choice of divergence affects both the learned network and results. Covariate shift between training and test may cause problems and can be handled by batch norm. Data under specification can result in overfitted models and must be handled by regularization and more constrained, generally deeper network architectures. So this is a pretty new lesson. And we also saw that dropout is a stochastic data or model erasure method that sometimes forces the network to learn more robust models, right? Any questions? If you got everything, just give me a thumbs up or raise your hand or something so I can move on. I have maybe 5 minutes left. Okay. All right. That's just 2 people. That's the rest of you. Guys, just raise your hands. I can count the number of people who raised your hands if you've got this. There are 23 of you. I'll wait for 10. 4 more, please. Please me. Okay. We capped out at 9, but that's okay, right? We'll also apply other heuristics. Continued training can result in overfitting to training data. So typically we track performance on held out validation sets. As you keep training, you're going to find that the error on training keeps going down. But at some point, this is not going to reflect on your test data. So we use some validation data and check where the validation performance is best. And you would use that model, which are early stopping methods for testing the models. This is something that you will often see. Here's another one that really matters. Often, the derivative of your loss is going to be very steep. And when the derivative is too steep, the divergence is going to be very steep. And this means you're going to have a sudden sharp change in your network parameters. This is saying your loss function is very peaky, and we don't like that. So to prevent this instability, again, this is a heuristic, we perform something called gradient clipping. If any derivative becomes too large, larger than some threshold, we cap it at the threshold. Typically, a threshold value is 5. So this is gradient clipping. Other heuristics, data augmentation. Often your available training data are going to be small. Or even if they are not small, the amount you have is not sufficient to train your dark model well enough, because you're always in a data insufficient regime. I don't care if you have 1 trillion training instances, you're still suffering from data insufficiency. And so we like to extend our training data by distorting examples in a variety of ways to generate synthetic labeled examples. For example, if this is an image of a Coca-Cola can, if I rotate it a little bit, or reflect it, or squish it a little bit, it still remains a Coca-Cola can. And so I can use all of these modifications of the original image as additional training samples to my network to virtually increase my training data. So this data and the manner in which any data instance can be modified depends on the kind of data. Scaling, rotation, distortion, things like that. You're going to do different things with images and audio and other kinds of data. But in every case, this mechanism of generating synthetic data from already available labeled examples is data augmentation and can make a big difference in how you train your models. And there are other tricks. You normalize the input. You normalize the entire training data to make it zero mean unit variance. This is like batch normal the input. You can play around with the initialization tricks. If you don't initialize your model properly, often it won't converge. And so many different initialization methods have been proposed, like Xavier, Chi-Ming, singular value decomposition, and so on. Another key point is that neurons that are identical at birth will remain identical at death. They will never diverge. And so we want to make sure that all of our neurons are distinct from one another. So overall, there's so many little tricks and so many little things you have to keep track of, that making models converge is an art form. And the only way you're actually going to become really good at it is through practice. And so here's how you'd set up the training problem. Obtain training data, use appropriate representations for inputs and outputs, choose a network architecture. More neurons means you need more data. Deep networks are better than shallow networks, but they're harder to train. Choose the appropriate divergence function. Choose a regularization. Choose your heuristics, batch, norm, dropout, whatever. Choose your optimization algorithm, for instance, Adam. Perform a grid search over hyperparameters, which includes learning rate, regularization parameters, and so on. Often on held out data, but in many cases, you can't actually, you don't have the luxury of having some held out data. You're just going to test it on some large set that you will call your test set. Yeah, I suppose that is validation data. And then train and evaluate periodic linear validation data, or at least stopping a quick one. And so in closing, over the past several lectures, we have outlined the process of training neural networks. With some history, we've given a variety of algorithms. We've talked about gradient descent-based techniques. We've spoken of regularization for generalization, algorithms for convergence, and various heuristics. So you're going to have to employ all of these, and practice makes perfect. I will stop here. And in the next week, we're going to change subjects and begin talking about convolutional neural networks. If you have any questions, I'll take them. Otherwise, we can over. Thank you.